And this time I'm going to remember to share my screen. Okay, for some reason I cannot share my screen. Here we go. Okay, so the last couple of, well, especially on Monday, but over the past week, we have been looking at models involving chance. And on Monday, we spent our time assessing models involving chance. And there is a process that we used. And today's lecture is mainly about formalizing that process and discussing how you make decisions at the end. But as always, we start with the announcements. This is the same set of announcements as on Monday. Homework is due tomorrow. You can turn it in by tonight. There's midterm information and a request that you please, if you need to take the alternate time offered, you must email the address on the screen by Friday. I have my own recommendation about the midterm. Lots of people are aware that it's a good idea to go over your homeworks, your labs, your projects. There we'll be posting a couple of old exams. But I can't overemphasize the importance of reading the textbook, especially on the current material, and especially the importance of not just skimming the words and focusing on the code. It's the words that are important. Okay, so when you watch, or if you re-watch video lectures, don't fast forward through everything until the notebook appears. Okay, actually focus on the place where there is a discussion, and then the notebook should make more sense. So for any logistical questions, please please post on Ed. Are there any questions that I can take about what's on the current screen? Will be more expert than I on some of the logistical issues. You guys seem to be very well informed about this. That's wonderful. Okay. So a recap of the weekly goals. On Monday, we assessed consistency of data and models that we had involving random chance. Why did we have those models? Because in the world in which the data came from, there was some expectation that the data had to be drawn at random, but they did not look like they had been drawn at random. So we assessed the model of drawing at random. And what we're going to do today is discuss that general process. You know, where does the model come from? What are the models that you are comparing? How do you decide what test statistic to use? And then what do you do with how do you simulate it? And then what do you do with the simulation at the end? On Friday, we'll use the same ideas, but in a different scenario, which is very common, where you have two samples, each of which comes from some underlying some population, and you're seeing differences in the sample, but you want to say, well, are those differences just due to randomness, or is it because they're actually reflecting underlying distributions in the two different populations? And so let us start by doing a recap of the last calculation we were in the middle of last time. And so that was an example about jury selection in Alameda County. And the California law says jury panelists have to be selected at random from the eligible population. This was the entire basis of Monday's lecture. And so what the ACLU of Northern California did was it actually looked at jury panels in Alameda County and compared with the distribution of the eligible population to see whether the panelists in fact looked like random samples from that population or not. And I'll just remind you of the data. They took a total of 11 trials in the Superior Court. There were approximately 1,500 panelists, and they compared the distributions of ethnicities of the eligible jurors and the panelists. Now, the panelists are those who are supposed to be selected at random. And so perhaps we should recall also that, so you have a categorical distribution of ethnicities of the eligible jurors, and then separately you have the same distribution but for the panelists. To see how close or how far those are, we have to we needed to develop a measure of how far two distributions are from each other, and that measure was called the total variation distance. The calculation is starts out pretty natural. First, you just look at the difference between the two, and some differences are going to be plus and some differences are going to be minus. Distribution 1 is going to be larger than distribution 2 for some categories, and the other way around for the other categories. And we noticed that the plus differences were exactly the same as the minus differences in total, because both distributions added up to 1. So what we did was we just, added up essentially all of the plus differences. And a way to do that is by taking the absolute value of each difference, adding up and dividing by 2. Now that is a lot of words. What I'm going to do is I'm going to go back to the notebook where we did this calculation. And while we redo the calculation, there will be scope for you to ask questions. Why do we divide by 2? Give me a moment. I'll talk about that when we do the demo. So let us go back here. All right. So those are the distributions of the eligible population of jurors and the panelists. And we saw by visualization, this is just a code that was used last time. We saw by visualization that the two distributions they appear to be different. The question now is, could such a difference have arisen due to chance? And so we created an array which had this distribution of the eligible populations in it, and we sampled at random from the distribution. Now, when you have multiple categories, sample proportions is the way to go. And it gave you the proportions in the sample, and we'll do it one more time and actually look at the distributions of the panels, the sample, and the eligible population. And it is apparent, as we saw last time, that the random sample looks much closer to the eligible population than the actual panels did. Okay, let me pause for a second. We haven't got to the total variation distance yet. Any questions thus far? Okay, so now we wanted to have a numerical measure of this difference, because we're not going to be able to look at tens of thousands of random samples. And so the natural thing to do was to take the difference of the percents of the proportions in each category. We noticed that the sum of the minus differences is exactly the minus of the sum of the plus differences, right? The plus differences are where, which direction did we do the minus? We did panels minus eligible. So the plus differences are where the gold bars exceed the blue. The minus differences are where the blue bars exceed the gold. And because both distributions have to add up to 100%, the plus differences in total have to be the same as the minus differences. So the key is actually the plus difference, which is 0.14, right? So what we wanted to get to is the 0.14. And one way to get that is to go to this table, look at everywhere the difference is positive and add up those. But another way to get that, since the other set of differences is exactly the same, but with a different sign, you take the absolute value, and then the pluses will still give you a 0.14, but the minuses will also give you a 0.14. And if you want the 0.14, you divide by 2. Okay, so now let me address the question of why do we divide by 2? So, if you just want a sense of which one's further, you don't have to divide by 2. You can multiply by 17. You can divide by 54. You can, use any unit of measurement. After all, when you measure a distance in inches, you can multiply by 2.54 and you'll get the same distance measured in centimeters. You can. However, this quantity that you are saying has an interpretation, just the sum of the positive differences. In later courses, you will see that this has an interpretation as the sort of biggest possible error you can make if you use one of the distributions to find a proportion rather than the other. If in the case of 2 categories, somebody asked already in the chat, do we only use this in when you have multiple categories? You can, of course, use it if you have only 2 categories. In the case of 2 categories, we'll see that dividing by 2 gives you something very natural. Okay, so hold the thought for now. And let's just go for the 0.14 plus difference. So we define the function to do that. Distribution takes 2 arrays, distribution 1 and distribution 2. Those are what you're comparing. You take the differences, take the absolute values, add up, and then divide the sum by 2. And our function gives the right answer for our distribution of panels and the eligible population. You can apply it to random samples drawn at random from the eligible population and compare with the 0.14. And so if we do this, the first time I run it, I get 0.01, which is about 1/10 of what I have in my among my panelists. And I'm just going to keep running this thing. And you're saying this 0.01. Basically, this is 0.01, 0.02, definitely not 0.14. Okay, quite a bit smaller. And so now, as always, we want to do this multiple times. So we will define a function that does what we just did, so that we can call the function multiple times inside our for loop. Now, why is that important? Because every time you call the function, it draws a new random sample, and therefore you get the distance corresponding to that new random sample, and that is why you get a distribution. Right? If you only use one random sample, you'll just have only one value of the total variation distance, which is not what you want. You want, as many possible values as you can get. Okay, so if I run this function over and over again, what the function is doing is it is drawing one random sample, looking at the distribution in that sample and calculating the distance from the eligible population. And so here we go. Distances. This is roughly 0.02, 0.01, 0.027, but still, we are not seeing a 0.14. Those of you who were here on Monday, do you agree that this is kind of where we left off? Okay, so this is where we had left off on Monday, and now maybe somebody could suggest to me, please, what should we do next? Yes, find lots and lots of these distances, run it multiple times. Exactly. And we do that by using a for loop. We will make an empty collection array. Let's just decide that we're going to do 10,000 repetitions in that case, 10,000 simulation in that case for index in an array that has that many elements. What are we going to do? Each time we are going to call this function, because each time that function is going to give us a new distance. And then we are going to append that distance to our collection array. So this collection array will get augmented every single time by a new call to our function. And if I haven't mistyped stuff, that should simply work. And so I'm going to run this thing. So before I run it, let's just be clear of what Python is doing. For each of the 10,000 times, it is taking a sample of 1,453 panelists from the eligible population, because 1,453 was the sample size of the panels. It is looking at the distribution in the panel and finding the distance from the distribution of the eligible population. And now, you know, we don't want to look at 10,000 numbers, we want to visualize them. So here's a histogram. And this histogram is the prediction made by the model of random selection, right? If you selected panelists at random, this is what the distances should be like. The distances are, of course, always positive because, or greater than equal to 0, because they're distances. They involve, the calculation involves only absolute values. But they, you know, about the biggest you got is kind of 0.04 something. What did we actually get? We got 0.14. And so now, what is the tension? The tension is that the panel was supposed to be selected at random, and in that case, the distances should come out like this distribution. But the reality was we got a distance of this much, 0.14, which is way out to the right-hand side. So what is the reasonable conclusion? Biased, not random. Okay, so yes. So the prediction is made under the hypothesis that the panel was selected randomly. The reality does not agree with that assumption. Now, when reality and assumptions collide, which one has to go? Assumptions, because you made those up, right? The reality you can't get rid of. Those are the data. So the reasonable conclusion here is that the panel was not chosen randomly. And once again, this is the same as the conclusion we made in the first example that we did with jury selection. And it is incumbent upon us to examine now why there was a bias. We did that in the previous example, and it's worth doing it again. First, quickly, let me summarize the method. You're trying to assess whether or not a sample was drawn randomly from a distribution. It happens to be categorical. The TVD is a good statistic because it measures the distance between two categorical distributions. There'll be the one in your sample that you generate and the one in the underlying population. So you sample at random, you compute the TVD lots of times, and then you get a distribution of all the TVDs that you'd have got had you been drawing at random. And then you compare that empirical distribution with the actual TVD. And in our case, the actual TVD was very far from the predicted distribution under random selection. So just by eye, we said, look, you know, these data are not consistent with the model of random selection. So why then? Recall that you start with eligible jurors in a county, and this is a description by law who is eligible to serve on a jury. And at the end, you end up with a jury. But in the middle, there is a selection process. Right, so you'll recall that all eligible jurors in a county, you don't necessarily have a list of all of those. So you have a list that you want to draw, that you draw from, and from that you draw a panel at random, And then from a panel, you select the judge and the legal team select by deliberate choice the final jury, often of about 12 people. So let me pause for a second and take questions about the way juries are formed. Anybody, any questions about those arrows that are there? Okay. So it is in this list is very important. In the, we're looking at 21st century selection, and this selection at random was actually attempted by software. The software was not the greatest, but it is definitely possible to improve software. Still, there was an attempt to actually select at random. But somebody just asked, were the lists complete? Well, let's see. The list of eligible residents, if you have ever received a letter, in Alameda County that you have to appear as a juror, you might know that the list consists of registered voters and those with DMV issued driver's licenses or California ID cards. And so there's the good news and the bad news about this list. The good news is that it is way, way, way more comprehensive and better and less biased than, do you remember the 1962 jury roll list in Talladega County, which consisted of what was it called? The personal and professional acquaintances of the commissioner. So this is a huge improvement over that, but it still excludes all those who are not on those lists. So could we have a little discussion about who might not be on these lists? So there are communities who might not be on this list, do not have exactly the clear definition is I don't have a driver's license or I don't have an ID card. I am not a registered voter. So I'm neither a registered voter nor do I have a driver's license. And who does that run? Typically that runs to people from communities that have lesser resources. And there is this lingering, lasting effect of systemic racism, that lack of resources is still associated with race and ethnicity. And so this is something, that we need to counter. But one of the things that we need to do is to make sure that everybody who is eligible has the opportunity to serve on the jury. Why? For two reasons. One is that the composition of the jury is a significant factor in the eventual verdict. And so therefore, for the defendant to have due process, the selection process must include all possible eligible jurors. But the other reason is that everybody who is eligible deserves the right to participate in the judicial process. It is their right to be considered for jury selection, and denying people that right is also inappropriate. So the ACLU recommended specific improvements, and we can think of many: greater outreach, follow-up for those who just do not respond to the summons. People who don't have a lot of resources, who have not registered to vote, who don't have a driver's license, they often don't have fixed addresses either. And I think if you recall, you often get like a letter that says you have to show up. And well, maybe the letter just doesn't reach. And so we have to follow up. And crucially, jury service for many people just isn't compensated. And if you don't have a lot of money, then the thought of committing many days to being on a jury is very difficult, because then, You still have to eat, you have to pay the bills. So there are many suggestions that were made for reaching all of the eligible residents, even though the list that is now used is pretty large. Okay, so what I would like to do now is pause for a couple of minutes for questions, and then we will work on generalizing the process that we have set up in the context of another example. The arrows, which one is random? It's this one, from eligible residents to jury panel. This one is supposed to be random. All right. So all of these decisions that are being made, was it 1453 was the sample size, that is the size of the panels that were studied. The population size was much, much bigger than that. Okay, so all of these decisions are being made under uncertainty, under incomplete information. And so we're trying to decide between two views of how the data were generated. And the thing that we have to keep in mind is, it's not necessarily always clear whether data are consistent with one view or the other. In our cases, it has been very, very clear, but we are going to have to make some kind of decision in the face of some uncertainty. And we have to keep in mind that random samples can be very extreme. It is not likely, but it is possible. And so therefore, it makes sense to set up, a system and some ways of making assessments with that we understand as data scientists. And the great thing about random samples is we can measure the chance that we're going to be off. Okay, and so that is going to be a focus of what we're about to do. And we're going to introduce the general terminology, which I've seen used in the chat, but we have not introduced it at all. So I would ask that we start afresh and think about the terminology from, starting with zero. And the process that we have gone through is called testing statistical hypotheses. It chooses between two views of how the data came about, and each of the views is called a hypothesis. It's something that we propose. And the test helps us to choose between these two hypotheses based on consistency with the data. And the context in which we are going to set up the terminology is genetic data gathered by Gregor Mendel, who is widely known as the founder of modern genetics theory. And he studied many, many plants, how characteristics were passed down as you kept breeding plants, and pea plants were a big part of his analysis. And that's why when Google had its Google Doodle for Mendel, you can see what plants they used. All right, so he had many, many experiments, and we are going to use just one of them. So one of his experiments involved particular kind of pea plant where the flowers were either purple or white. So every plant, the flowers were either purple entirely or white entirely, but no plant had both purple and white. Okay, so based on what he was understanding about how characteristics were passed down, he proposed a model, which is that each plant is purple flowering with chance 3/4, regardless of the other plants, that a chance is not affected by how many other purple or white plants you have around. And so there are two views of the world, right? The model's good, the model's not good. So these are two reasonable views, and we should be able to work out, we can develop a process for seeing whether we can figure out which of the two views looks good. Now, needless to say, if we are going to answer this question, we have to look at some data. I mean, really, we should grow some pea plants. Luckily for us, Mendel grew them. And so let's take a look at his plants now. Okay, so his model for purple-white is draws at random with replacement. Remember, he said it doesn't matter what the other plants came out. Each time you have chance 0.75 of getting purple. So we put that in a list that has 0.75 for purple and 0.25 for white, and we call that Mendel proportions. And now here are his data. So he grew 929 of these plants. And what he observed was that 705 of them were purple flowering. So very natural calculation is then what percent is 705 out of 929? And that is 75.9% roughly. Yeah, you know what? He said 75, it's 75.9, maybe it looks good, but immediately the question arises, well, can you have a difference as large as 0.9? Maybe you can, maybe you can't, depends on the sample size, we have to see. So before we get into details, let's just note what the hypotheses are. The hypotheses, just in plain language, are his model's good, his model's not good, right? And now we have some language. Okay, one of the hypotheses is called a null hypothesis. If null is, it really means nothing is going on other than chance. So this is a completely specified chance model about how the data were generated. And for us, in practical terms, this is the model under which we can simulate samples. And when we do that, we will say we are drawing under the null hypothesis, and we will be lazy often and say we are drawing under the null. So in this particular context, the null hypothesis is the plants are like draws at random from basically a box that has 3 purple plants and 1 white plant, and you're drawing at random with replacement. That is the representation of the model that, and this, you can see clearly that we can use this to simulate. Okay, the other hypothesis is brilliantly called the alternative hypothesis. Okay, and what is the other hypothesis? Model is good versus, what's the other view? Model not good. Exactly, very good. So there is a different view, and in this case, it's just that it's not good, and it's very important for you to note that it's not saying in what way not good or why not good. It's just saying the model is not good. Okay, so we now need to think about something we are going to calculate that will help us tell whether the model is good or not good. And so this thing is called a test statistic. We've been calling it a statistic throughout, but since it's being used in a test, it's called a test statistic. And it is the quantity that we choose to simulate to decide between the particular null hypothesis and the particular alternative hypothesis that we have. Now, in this case, or in any case, we have to ask ourselves, what kinds of values will make us lean towards one hypothesis and what kind of values will make us lean towards the other? Right, so whatever number it is, preferably we should end up with a statistic where we say, you know, small values make us lean towards one and large values make us lean towards the other. So our recommendation is that you generate your statistic in this way. If your statistic is such that you say, well, very large values could make us think that it's the alternative, but also very small values could. Almost certainly you have not noticed that you could just take a distance and absolute value. And so in this particular case, it is very natural. We started with 75.88, right? That was the percent that was observed in the sample, and the model was 75. So if the percent observed in the sample is either much larger or much smaller than the 75, then you have evidence against Mendel's models. And so what we're noticing is that it's the distance from 75 that's the issue, not whether it's more or less. The model is either the hypotheses are model good, model not good. And so a natural statistic is just look at that distance. You have a sample percent, you have 75, just look at that distance. All right, so to everybody who's having a very technical discussion on the chat, may I request that we pause on that? We will talk about all of that. What I would love for you guys to do is to be able to explain all of this in English without any jargon, because that is the job of a data scientist. Okay, so all of you who have been asking, why do we divide by 2? Why do we divide by 2? Why do we divide by 2 in the total variation distance? When you have two categories, just two, so in this case, purple and white, if you calculate the total variation distance, this is the number that you will get, provided you divide by 2. If you divide by 17, you will get something else. Okay, so a division by 2 actually gives you something very natural, and the reason for that is explained in the textbook. For now, I think you'll agree that this is a natural statistic to look at. If this statistic is large, that is evidence against Mendel's model. So let us go ahead and calculate the, okay. So in the sample, we had an observed percent, and then Mendel said 75. So the distance that we observe between those two numbers is 0.88, and that's this 75.888 minus 75. Okay, and if we sample under the null hypothesis, we will get a whole bunch of other proportions, and we'll have to figure out this distance. And the right thing to use is you are sampling from a categorical distribution and just looking at the proportions. So you use sample proportions. And what do we call it? We called it Mendel proportions, is what we're sampling from. Okay, so if you assume that the null hypothesis is correct, Mendel's model is good, then this is how the plant should come out. And so I'll just run this cell a few times, and you can see, I hope your eyes are going to that first item, right? You're looking at the percent of purple flowering. You're looking at the proportion purple flowering. And we can easily convert that to a percent. So let's do that. So that is the array of both purple and white. We need item 0. That gives us the proportion of purple, and then we multiply by 100 to get the sample proportion. And now we return the absolute difference between the distance between the sample percent and Mendel's postulated percent of 75. And if I run this, if I call this function multiple times, every time I should get distances. And remember, our distance was 0.88. Now I keep running this. Actually, don't you agree that our distance is looking pretty good compared to this model? What do you think? Yeah, so we'll do the usual thing, is we will run a for loop to simulate the distance multiple times. And so we have our empty collection array, and we append the array with a new call to the function every time. It is important to do that because that way the function gives us a new distance every single time. And since I'm going to use this many times, I've given the table a name, and here is the histogram that you are all waiting for. Okay, so that is the prediction under the null. Why don't we divide by 2 here? We didn't actually compute, well, it turns out to be equal to the total variation distance, but we actually just looked at the distance between the percent purple. Since there are only two categories, the distance between the percent white is going to be exactly the same. Okay, so this histogram is important to understand because it is a prediction. So you simulate, you say, pretend the null hypotheses were true, then what would the statistic look like? You get the empirical distribution of that. All right, so it's a prediction made under the null hypothesis. On the horizontal axis, you have all of the likely values of the statistic, and the percents, the proportions, the areas show you how likely those values are under the null hypothesis. Okay. And of course, we only have 10,000 repetitions. If you did 100,000 repetitions, you'd get a slightly different histogram, but good enough for our purposes. Okay, so that was the prediction made by the null hypothesis. And now, based on your experience, I know you're itching to put the 0.88 down. What was the 0.88? The 0.88 was the statistic that we actually observed. And look at that. Model, this is the data point, this is the prediction under Mendel's model. Do these data look consistent with Mendel's model or not? Yes, because that point is right in the heart of the distribution. All right, notice that your eye can see that even if you ignore completely the numbers on the two axes. You're just looking at the shape. This is going to be very important in a few minutes when we decide how to make this decision. That it really depends on, is it near the bulk of the area or is it not near the bulk of the area? That is what we are seeing. And so what you are judging is consistency between the observed point and the prediction made by the null hypothesis. And that is the thing that allows you to make the decision. So the decision here we made by eye, and it's somehow very apparent that this is consistent. In the case of the jury selection examples, it was very apparent that those realities were not consistent with the data. The data were not consistent. By the way, let me just say something, as people keep asking me, why do I say the data were plural? Because the word data happens to be plural, and I just used to remembering that. So the logic is, to resolve the choice between the two hypotheses, you compare your observed test statistic, which is the one that came from the actual sample, and the distribution that you generated under the null hypothesis. And if your observed value is not consistent with that distribution, then it's the hypothesis that has to go. So that is where the technical language rejects the null hypothesis comes from. And now you have to decide whether a value is consistent with the distribution. And sometimes you can just see, but other times it may not be so clear. So we have to actually try to recall what our eye was doing when we decided consistent or not consistent, right? And what we are saying is, is the point, the observed point, sort of in the bulk of the distribution, or is it very far out? And in other words, is it in the center of the distribution, or is it in the tails? And so looking at the tails was a very important criterion. And so let me define what I mean by the tail. You start at the observed value of the test statistic, and you look in the direction that makes you think, oh, maybe the alternative is the way to go. So in the case of Mendel's model, let's just check. We start at the observed value, but large values of the distance will mean that the model is bad, because we are looking at a distance from the model. So we start where the observed value was and we look right. And what our eye did was, it said that we start here, all of this stuff, which would make us feel that, distance is large, is actually pretty likely under the null hypothesis. So, this point looks consistent with the null hypothesis. If in another situation, you were testing, and I'm just going to take an example. Supposing you were testing whether a coin is either fair or biased towards tails. Okay, so you have some reason to think that this thing is biased towards tails. It doesn't give you a lot of heads. So your null hypothesis is that the coin is fair. Why is that? Because that is the hypothesis where there's a specific chance of heads, 0.5. You can simulate under this hypothesis. Your alternative hypothesis is the coin is biased towards tails. You're not saying how biased. So you actually can't simulate under this hypothesis. Your simulation has to be done under the other one, and that's the one that we call the null. Okay, so now suppose you decide I'm just going to use the number of heads as the statistic. What kind of values of the numbers of heads will make you think, maybe alternative? Large numbers of heads or small numbers of heads? Small numbers of heads, because if the coin is biased towards tails, then you should have a small number of heads. Yes. So what you should do is start at the number of heads that you saw and look to the left-hand side. Let me pause for a second and ask you if you understand what the tail means here. All right. So then, okay, so now look at this tail. Do you think it's big or do you think it's small? Okay, so somebody said no. I'll come and talk. So let's look at this histogram. This is a prediction of the number of heads by a fair coin. Our number of heads came out here, right? So can I ask, does the coin look fair to you or not? So some people are saying yes, some people are saying no, but the point is that the number of heads that you got looks less than what you'd expect by tossing a fair coin. So this kind of points you in the direction of the alternative. You're not sure you want to go there yet, but this is certainly in the direction of the alternative. What you say is, I'm going to look at the area, the proportion of outcomes that were this number or even less. So even more in the direction of the alternative. And you can see we quickly had this sort of disagreement between, yeah, it looks fair, no, it doesn't look fair. And so, you know what? It is important to get used to the fact that this is now really up to your judgment. If you think that this is too far out in the extremity of the distribution, you can make the conclusion that your coin is biased towards tails. And if you think, yeah, you know what could happen, then you can say, well, the data are consistent with the coin being fair. It's up to your judgment. And with great power comes great responsibility. And I know that at this point, people are getting very, very nervous. My goodness, I have to make a judgment. No, 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 give me a rule. Give me a rule, give me a rule, give me a rule. Okay, well, so we'll give you a convention. It is only a convention. So you're looking to see whether the statistic is far out in the tail, and it has to do with, you have to make some definition of how far is far. Right, so there's one convention that says you look at the area of the tail. If the area and the tail is less than 5%, you say, okay, that's small. And you call the result statistically significant. There is another convention that says if the area and the tail is less than 1%, which means the point is even further out, then you call the result highly statistically significant. And this is all fine. These are conventions that are often used in such analyses, and it's very, very important to keep in mind that they are just conventions. You do have the right to decide any kind of cutoff you want to decide for small. What you should do is you should provide your observed statistic. You should say what you are using as the cutoff, and then your readers can make their own decisions. You should not just compare with 5%. Okay, so somebody said, well, are we ever going to use a p-value? Yes, we are. This proportion that we calculate, the proportion in the tail to compare to 5% or not, or to compare to any cutoff we have, that is called the p-value. I'm actually going to stop here. There we have a definition of the p-value, and we have a discussion of what it means and what it can be used for. We'll start Friday that way, and then go on to applying all of what you've learned in a different context. So I am actually going to not start a discussion about what the p-value is right now. Okay, so let me stop the recording.